I'm going to throw a ball against a surface, a wall, and in fifth period, I kept saying throw a ball against a wall, and the wall hitting the ball, and the ball hitting the wall. They started to snicker, so I started to change my word from wall to surface, but you're still just throwing a ball against a wall, and I get that it rhymes. But let's say we throw the ball at 5 meters per second. The ball is in contact with the wall for perhaps 40 milliseconds. And then recoils off the wall at 2.5 meters per second. So if I was to ask, and by questions, these are just exercises. They are not problems. Problems usually require multiple steps and maybe some figuring. These are exercises. They're just plug and chug. So what is the impulse experienced by the ball? And what is the force experienced by the wall? And finally, how much work was done on the ball? Answers are on the board. The question. So the fact that they asked specifically for impulse kind of helps. So I'm going to think on impulse for a minute. There are two parts to impulse. There's force times time and change in momentum. They both equal impulse. Look, I see mass of the ball and the velocity of the ball very clearly expressed. So it seems to me that change in momentum is the way to go. Time has been given to me too, but nothing about force has been given to me directly. So I don't think I'm going to calculate force times time to get the impulse. So with that, I'm going to use delta P, which is m v final minus m v initial. And I'm not putting those vector bars on top for my health. It's a reminder that I have to pick direction and stick with it. I'm going to choose to the left to be the positive direction, which means m 0.15 v final, which is 2.5, minus m 0.15 v initial, which was to the right, so negative 5. Common mistake, and I even heard people say that they got something different. They got it different because you didn't take direction into account. And this will give you positive 1.125. It's positive, and it's kilograms, meters per second, but the positive means to the, I guess, left. Now, I do have the impulse on the ball. So the force on the ball times the time, 0.04 seconds, that's in contact with the wall, has to be equal to 1.125 kilograms meters per second. So I think I can find the force on the ball just by dividing out the time. And that tells me the force on the ball is 28 kilograms meters per second divided by seconds. It's kilograms meters per second squared. That's a Newton. But that's on the ball. Wow. Newton's third law would tell me that the force on the wall must be equal but opposite to this. So the force on the wall will be 28 newtons to the right. Newton's third law. Work done on the ball. Well, work can either be force times displacement, or force dot displacement, or change in kinetic energy. Although I do know a little bit about the force on the ball, I don't know anything about any displacement. And I don't think the wall moved. We could say the ball might have squished and its center of mass moved during this time, but I don't think we have a reasonable way to figure out how much. But we know the initial and final velocity, so we know the change in kinetic energy. So as a quick example, I'll just do 1/2 mv final squared minus 1/2 mv initial squared. This should give me the change in kinetic energy of the ball, and that would be the work done on the ball. It works out to be negative, I think, 1.4 joules. And that makes perfect sense. The ball lost energy. It's traveling slower than it was before. Again, this is the start of where we're going to go for the next couple of minutes, but I want you to consider that the arrow can be affixed with different tips, and that these different tips allow for different outcomes. For example, one of the tips, blunted, causes the arrow to bounce off. Okay. A different tip causes the arrow to stick to the pumpkin. And another one causes the arrow to pass through the pumpkin. So 3 different possibilities. Let's assume that we fire the arrow the same way every time, same velocity, and that the mass of the arrow does not significantly change, nor does the mass of the pumpkin. In each case, the arrow can either bounce off, pass through, or stick to the pumpkin. In which case would the pumpkin experience the larger impulse? There's no equation here. I want you to explain your answer, but you need to do so in such a way that you can earn all the available points. And we'll see if you can get all the points. Take 4 minutes. Talk to each other about this one. I am going to call out students today, so you might be made to feel uncomfortable. In choosing A, that's fine. But your argument, almost all of it, had to do with the arrow. But the question was about the pumpkin. So there might need to be something in the end where you address the pumpkin. But let's stick with the arrow for just a few minutes. Your choices have to do with the parts of impulse that are either about force and time or mass and velocity. And yeah, we've got direction here too. Let's handle an easy one. Did the mass of the arrow change?
No.
All right. Did the initial velocity of the arrow change?
No.
So nothing about that term changed at all, correct? So now we've narrowed down that it has to be something about this velocity that's controlling it. So one of the things you probably should state to make sure the judge knows that you are aware of this, that the only thing that is different in all 3 of these scenarios is the final velocity of the arrow. Do you follow where I'm going? Address the fact that the mass of the arrow didn't change. Because if the mass of the arrow had changed, it could affect the outcome. Remember, the thing is you're trying to identify and isolate what has changed and what has stayed the same. So if your conversation wasn't going to address the mass of the arrow staying the same, you're probably not earning that point. So now let's handle the bouncing back. And you don't have to use math here. What's more challenging to do? Slow something down or stop something, turn it around, and send it back? you can make a reasonable argument that slowing something down isn't as difficult to do as stopping it and returning it. That's a reasonable argument to indicate why bouncing off would have a greater impact on that final velocity than just slowing it down. You can make a numerical one, but you don't have to. You can make a reasonableness argument. Now that tells us that the impulse on the arrow is greater for A. It doesn't tell us why the impulse on the pumpkin would be greater for A. And that probably comes down to talking about maybe this portion. Because we don't know anything about how the pumpkin recoiled. I don't think the pumpkin just sat there and took it. I think the pumpkin recoiled. In fact, I think if it's connected by a string, the pumpkin probably swung upward, something like that. But we're talking about the impulse experienced by the pumpkin that is occurring right as the collision is occurring. So how do we relate the impulse on the arrow to the impulse on the pumpkin? I think we can do something we just talked about. We can talk about the fact that the force on the arrow is got to be the same size as the force on the pumpkin. That has to be true, Newton's third law. In fact, if I want to bring in Newton's third law to this, I could probably put out there that they're equal and opposite. That's Newton's third law. That's not enough, though, because impulse is force and time. You're going to have to address time. And is the arrow in contact with the pumpkin longer than the pumpkin is in contact with the arrow? I mean, is there any way for you to be in contact with the desk without the desk being in contact with you? No, right? That's the whole point here. In fact, there is no way for an object to apply a force through contact that doesn't require the same amount of time for contact. So I think you can make the reasonable argument that for every impulse, there's an equal and opposite impulse. That's not just this question, that's all questions. For every impulse, there's an equal and opposite impulse. Because every force, there's an equal and opposite force. Now that impulse may not do anything to the object. When the ball strikes the wall doesn't recoil. Because there's other forces acting on the wall at the same time that keep the wall from moving. On the other hand, I think the pumpkin's going to move. Do you guys agree? I want to do something with you real quick, and you're probably not going to understand why in the beginning, but I want to derive something for you, okay? So I'd like you to kind of follow a quick argument. This side is about the arrow, and this side is about the pumpkin. All right? First, I want to use the definition of impulse. And if the impulse on the arrow is equal and opposite to the impulse on the pumpkin, then delta P for the arrow has to also be equal to minus delta P for the pumpkin. Now, this is only true if the pumpkin is free to move. If the pumpkin is experiencing other forces that hold it in place, this wouldn't be true. But we're talking about an object that is free to move. Now, definition of delta is final minus initial. So this could be the final momentum of the arrow compared to the initial momentum of the arrow. This will have to be the opposite of the final momentum of the pumpkin compared with the initial momentum of the pumpkin. We all good so far? All I did was use the definition of delta to put final minus initial in place. Now I'm going to distribute that negative sign. Distribute the negative sign. It's no big deal. I know I'm writing it all out, but I expect that you guys can do this basic algebra stuff. Now, you may not see why I want to do this, but I want to get all the initial stuff in one place and all the final stuff in another place, okay? So I'm noticing that this one's negative, so I'm gonna move it to the other side. And this one's negative, so I'm gonna move it to the other side. So we're just gonna kind of do one of those. Move those around. So that'll give me now, I don't know if you're seeing what we've assembled here, but this is before contact, and this is after contact. And what it should be communicating to you is that the momentum of the entire system before there is contact has to be equal to the momentum of the entire system after there's contact. If Newton's third law is to be believed, it predicts that momentum should be conserved. That's what it's stating here. Now, there's some caveats, kind of. But it says if you add up all the momenta of a system before a collision, it has to be equal to all the momentas of a system after the collision. And we're going to call this conservation of momentum. Conservation of momentum is an incredibly powerful idea in physics. It is probably more powerful, or at least as powerful, as conservation of energy. With one important distinction. There's not multiple kinds of linear momentum. Objects have momentum if they're moving, period. You don't have to ask yourself, is the object above the reference level? Is the object pressed up against a spring? If the object's moving, it has momentum. And if there's an interaction, the momentum before is equal to the momentum after. Now, you're going to have trouble with this because this will not be true if there's an external force acting on the objects of your system. I'll say that again. This is not true if there's external forces acting on the objects of your system. If you bounce a ball against the wall doesn't recoil. The wall's momentum doesn't change. That's because the wall is experiencing an external force that keeps it in place. So momentum won't be conserved under those circumstances. You could even make an argument, well, the pumpkin is experiencing an external force. True, it is. When we talk about collisions, we generally talk about the instantaneous moment before contact and the instantaneous moment after contact. That's on purpose. Because when the arrow strikes the pumpkin, immediately after contact, the pumpkin will have a velocity to the right because it's not being held in place. It is going to experience a force that's going to cause a change in its motion after it starts moving. But instantaneously after the collision, the momentum before is equal to the momentum after. This is how collisions work. Now, there are lots of collisions. And notice, we didn't have to know if the arrow bounced off, passed through, or stuck to the pumpkin. This is true regardless of the circumstances of the collision. So if it stuck to it, this would still be true. If it bounced off, this would still be true. Regardless of how the collision takes place, the momentum of all the objects before equals the momentum of all the objects after, which I've repeated now 4 times. Now, I want to demonstrate a little bit of that, but to do so, I need to kind of refresh your memory about something. First, impulse is actually based on an integral. Got to remind you about that. And don't be too worried about it. This is only true if the force acting on an object isn't constant during the time interval. But for collisions, that's often the case. But I need you to remember something kind of more. If we have a situation in which the force isn't constant, we still have access to other things we've talked about. For example, if I plot force times time, and I have a situation like this, where the force increases, stays the same, and then decreases. The force is changing, so I clearly couldn't figure out the impulse without using calculus unless I recognize that the area under this curve is going to be the product of force and time. That suggests that the area of this graph is impulse. So if the object's mass doesn't change, I can tell you how fast it's going due to a more complicated force. This next thing, though, might be a little bit harder for you to understand. Net force equals ma. Now, we've talked about this a lot, but for an object whose mass doesn't change, an acceleration graph is going to be the same shape as a force graph. So looking at acceleration is like looking at force. You follow along? So if you multiply an acceleration graph by the mass of the object, you have a force graph. Everybody understand that? I'll say it again. If you multiply the acceleration by the mass of an object, you have a force graph. And the last thing I want to do is I want to talk about the way Newton actually formulated physics. It's a little different than what we talked about in class. All of these are Newton's laws, except Newton didn't formulate things the way we teach them to you. I want you to look at this relationship right now. This assumes a force that is changing over some time interval. So I want to pick a very small time interval and talk about just a small change in momentum. During a infinitesimally small slice of time, the force is constant for that instant. That's the whole point of the integral. So we add a bunch of those together while the force is changing, and that gives us the total change in momentum. So if I have a long interval, I can just look at the change in momentum, and it would be this integral. But if I want to look at a very small change in momentum, 1 dt, not a whole sum of them, but 1 dt, I could write that the change in momentum is one constant force times one slice of time. Is that okay? Now that's summing them over a large change, just one instant. You can solve this for force. And if you do, there's a lot here to unpack, but this is Newton's second law as it was originally written by Newton. He didn't talk about mass and acceleration. He said that it takes an unbalanced force to change the momentum of a system. He believed in integrating the idea of mass into all computations as it was a measure of an object's inertia. He believed in inertia to be a powerful subject within physics. So his second law wasn't net force equals ma. The way he wrote it was net force equals the rate of change of momentum. That's the way Newton put it out there. Now, it is quite plausible to be given a function that is momentum as a function of time. Its derivative would be a force as a function of time equation. It's unlikely to see that, but it wouldn't be too unlikely to be given velocity as a function of time and be prepared to multiply it by mass, because that would give you momentum as a function of time. We've seen quite a few velocity as a function of time equations. You multiply it by mass, you suddenly have momentum. Take the derivative, you now have net force. So I know it's a lot of points to connect.